the wonderful talk by Devalia today. Devalia is one person who has actually raised the prestige of CSA in the algorithmic world. And so after his excellent talk today, so we will have an equally exciting talk by Arnab. And I'm really happy that I have been called upon to say a few words about Arnab. So to me, Arnab is in the IT world, they have this phrase called full stack professional. So for me, I think Arnab is a full stack theoretical computer science researcher. I think he has touched all areas in theoretical computer science. And I have seen very few versatile researchers. There is tremendous depth as well as breadth in what he has worked on. Actually, the trajectory of Arnab to National University of Singapore, where he's currently a faculty member in the School of Computing, started off with UG and PhD at MIT. It took him to Princeton University for a postdoc, and he played a lovely innings at the Department of CSA for 5.5 years, or 6 years, 5.5 years at CSA. And that was the phase when I got to know Arnab rather closely, and I consider myself fortunate to have co-advised a student, Palash, who went on to win the ACM India Dissertation Award. And much of the award was actually due to the guidance given by Arnab. So I think Arnab, in the stack of his competencies now, I think the top of the stack contains problems like property testing. He's also looking at causal inference and also distribution learning and so on. So today he will be talking to us about model counting meets F0 estimation. I think I'm delighted to invite Arnab to give the talk. Let's give him a mic of applause.
Okay, thank you for that lovely introduction. Is the mic on? Yes. Hello? Okay. Yeah, it's always a pleasure to be here. Today I'm going to talk about a paper which kind of combines topics from two different areas, and that was the surprising aspect of this work. So the main point of my talk, sorry. Yeah, the main point of this talk is really to show this connection. And it's one of these rare works that once you understand this connection, I mean, the work is really actually very technically light. I think even like a motivated undergraduate could fully complete all the details of the paper. So this work is joined with Pawan Adudi at Iowa State, N.V. Vinod Chandran at University of Nebraska-Lincoln, and Kuldeep Neal also at NUS. So the R indicates that the author ordering is randomized. So we used, there's a, so in this American Economic Association, AEA, they have a tool which you can use to randomize the author ordering. And there's a certificate which certifies the randomness. So you can go and see that actually the author, I mean, there's one coin of one coin cost which generates the randomness, and that is stored there. So we use that, and none of us are student authors, so we try to make the author ordering randomized. This paper appeared in Fonts in 21. Okay, so let me just jump into it. So there are two different topics to talk about: model counting and F0 estimation. So let me first define both the problems. So both of the problems are fundamental in their own areas. So one problem is model counting. So in model counting, the situation is that you have a Boolean formula. So phi is a formula over n variables x1 through xn. And sol of phi will denote the set of satisfying assignments of this Boolean formula. Okay. So in the formal methods community, sometimes there are satisfying assignments are also called models of the formula phi. And the model counting problem is to find the size of the set, so the number of distinct satisfying assignments for this formula. Okay, and so just a quick example. So suppose the formula is x1 or x2, then there are three possible satisfying assignments. So you need to make one of these two variables true. So the only assignment which makes both of these variables false is excluded. So the other three assignments are satisfied. Yeah, so exactly finding the size of this set is sharply complete, but often we are interested in approximation. So this epsilon delta approximation means that you want to find the size of the set up to a 1 plus or minus epsilon error, a multiplicative error, with probability 1 minus delta. So for example, if both epsilon and delta are 1%, you want to find the size of this set up to 1% relative error with probability at least 99%. And right, so in general, this is hard to find exactly and also hard to approximate. So one motivation is actually minimizing the number of NP queries. So if you have access to an NP oracle, so one has SAT solvers nowadays which can solve satisfiability queries efficiently. So one question is how to minimize the number of NP queries in order to approximate the size of this set. One can also look at restricted types of formulas. So for example, for DNFs, there are classic algorithms which you study in randomized algorithms classes, like the Scarp-Luby algorithm, which approximates the size of the solution set in polynomial time. And in this talk, you will see a different approach towards designing approximation algorithms for counting solutions to DNF formulas that use a connection to streaming algorithms. Okay, so, and model counting as such has a wide variety of applications. It has been used in many different areas over the last 30 or 40 years. So now let me turn to the other problem. So this comes from a completely different area, from the topic of data streaming algorithms. So here the idea, the input is described by a stream of elements. Okay, so here you have the stream A1, A2, A3, A4, etc. And the idea is that there's some monitor which is sitting and getting as input this stream of elements. Okay, and the F0 problem in the data streaming world is to find a set of distinct elements in the stream. Okay, so I'm writing it like this. The union of AI, it's a bit of, it's not exactly correct, but what I mean, so if you think of each AI as being a singleton set, then this union of AI is really just a number of distinct elements. Okay, so I want to find a number of distinct elements in the stream. Okay, so just a simple example. So if your stream looks like this, the number of distinct elements is 4, right? So F0 of A is 4. And again, this is a fundamental problem in databases and in the streaming community with a long line of work. And the problem here is really finding a streaming algorithm that minimizes the space complexity. So of course, you could always just keep an exact histogram of the data that comes in. I mean, so whenever you see an element, you check whether you have seen it before or not, and then use that to count the number of distinct elements. But that takes space which is the size of the universe. So if the elements are coming from a universe of size n, right? So these numbers would be any numbers between 1 through n, then the naive approach, which would just keep a table of size n. I mean, and you keep track of whether you have seen the ith element or not in the ith slot of the table, that would take say size n, right? Space n. And the concern in the database community or the data streaming community is to find an algorithm to approximate F0, which minimizes the amount of space that's used. And again, this problem has a long history, like I said. But the one commonality which has kind of underlined algorithms for both model counting as well as F0 estimation is the use of hashing. Okay? And this has been there from the very early years. I mean, so model counting, there's a influential paper of Stockmeyer from 1983, which introduced use of hashing for model counting. And I mean, hashing has been used both in theoretical papers as well as in practical papers in the SAT solving and model counting community. And also in F0 estimation, starting from this foundational work of Lajoie and Martin in 1985, hashing has been a consistent theme. Okay, and we show that to some extent this is not coincidental. One can use algorithms for F0 estimation to do model counting and vice versa. Okay. All right. Okay. So let's just take a step back and think about how to count objects efficiently. Okay. So suppose you have you're trying to count the number of red dots in this picture. Okay. So and I want to do so in a way that minimizes the complexity of the procedure, say the space complexity or the time complexity. So the idea behind hashing is that you partition the space randomly in some way, so that the dots are almost equidistributed in the different cells, and then you take one of the cells, you count the number of dots in the cell, okay, which presumably will take much smaller time or space than counting all the dots in the whole area, and then you multiply by the number of cells. This is the basic idea. And so there's a particular algorithm for model counting which is called approximation. So I'm just going to describe at a very high level how that works. I mean, there are other algorithms in the same theme, but suppose these dots represent solutions to some Boolean formula. Okay, and so what you first do is like you count. So there's some primitive which allows you to count whether the number of solutions is at most some particular threshold or not. Okay, and this takes time, which is time or space, which is proportional to this value of the threshold. So you just count if you have more than threshold number of solutions, you just stop and say no. So if the answer is no, if you have more than threshold number of solutions, you partition the space into two parts. You again check if the number of solutions is at most threshold. You do it again. You keep doing it until you find a cell where the number of solutions is less than or equal to the threshold. Okay? And so this depends on both the procedure. I mean, the complexity of this process depends on both the depth of this recursion, so how many times you do the partitioning, and also the complexity of finding out whether the number of solutions in a particular cell is at most thresh or not. Okay. All right. Yeah, and again, the final estimate is just the number of solutions times the number of cells. So there are two kind of so if you're looking at a kind of a meta algorithm which works along these lines, there are two challenges to address. So first is how to partition into roughly equally small cells without knowing the distribution of solutions. So I mean, if you had if each cell had the same number of solutions, then that estimator would be exactly correct, but you want an approximate version of this, and also how many times you need to do this partitioning. So how many cells would you? Okay. Yeah.
The specific problem of counting solutions for Boolean functions is rather general. You could have pretty much encoded a lot of number of independent sets of a graph, number of colors.
Right. Yeah.
So it's just very general.
It's a very general, yeah. So, right. So we are going to use, so for very, as I said, I mean, if the formula is completely unstructured, then we are going to use queries to an NP oracle. But the more structure you have, I mean, then you have the potential of using faster algorithms for example, for DNFs, like I said, I mean, you can convert this, the strategy I'm going to describe, you can get a polynomial time algorithm using that strategy. But of course, for general formulas, that's not possible, and there, it depends on the exact problem. Okay. So first question is how to do this partitioning into cells in which the solutions are approximately equally distributed, and a very classical approach towards solving this issue is using pairwise independent hash functions. So let me just quickly recall for you what pairwise independent hash functions are. So if you have it refers to a family of hash functions. So this family is H. So it's a family of hash functions, each function mapping n bit strings to m bit strings. And the property we insist is that for any two keys, so for any n bit strings, y1 and y2, and for any two particular hash values, alpha1 and alpha2, if you choose a hash function randomly from this family, then the probability that y1 hashes to alpha1, let me say it this way. The probability that y1 hashes to alpha1 and y2 hashes to alpha2 is 1 over 2 to the m squared. Okay, so these events, y1 hashing to alpha1 and y2 hashing to alpha2, these are independent. Okay, so for any pair y1, y2, and for any pair alpha1, alpha2, this is right. And there's a very simple construction of pairwise independent hash functions, and this construction is going to be important for making the connection be efficient to model counting. So here, okay, so how do you construct independent hash function, pairwise independent hash functions? So one thing is that you can pick every x, so you can construct these XORs. Okay? So you take, so for deciding any bit of the hash value, you take every xi with probability half and you XOR them. Okay? So here, for example, I've chosen these x1, x3, x6. So the expected size of each XOR is n over 2. And then each XOR, so each choice of the bits that you XOR generates 1 bit of the hash value. Okay, so you have m of these hash values, and you do m of these XORs, and each determines a different bit of the hash value. Okay? So this basically reduces to a linear system. So computing the hash of x is equivalent to multiplying x by a matrix, an n by m matrix, and doing it mod 2, doing the matrix multiplication mod. Okay, so first so with that background, let me tell you the connection from F0 estimation to counting. So I'm going to describe a particular algorithm for approximating the number of distinct elements in a stream, and we're going to use that to approximately count the number of solutions to a Boolean problem. Okay, so let me first tell you a sketch of many of these. Sketch kind of, you shouldn't use that, but kind of a meta algorithm for F0 estimation. So generally you do something like this. So you choose, you have some set of hash functions, and you choose h randomly from the set of hash functions, and you keep this data structure, which is called a sketch. And what you do is for every element of the stream that you get, so AI that you get, you have some updating process, okay, which takes in the current sketch, the hash function, and the element that you have just observed, and that updates the sketch S. Okay? And you keep this, you do this update every time you see a new element in the stream. And finally, there's some way to estimate, to get the estimate of F0, okay, just from the sketch. Okay, and you return that estimate. And just for concreteness, let me tell you about two different algorithms for doing this update procedure. So one is called the minimum, and the other is called the bucketing. So let me tell you about the minimum one, which is very simple. So all that you do is you keep track of the minimum hash value. Okay, so you have some ordering among hash values, so you can look at, say, lexicographic ordering among the hash values, and you find the minimum hash among all the hashes that you have seen. Okay, and ultimately what you do is you return 2 to the n over min hash. Okay, and the idea basically is that, so for example, so maybe easier to think about is, suppose you are hashing to real numbers in the interval 0 to 1. Okay, so you would expect that. So if you have k distinct elements, so you'd expect that the minimum of the hash values would be at 1 over k. So the hash values would kind of equally partition the interval from 0 to 1. So 1 over k would be the minimum hash value, and so 1 over that would give you an estimate of the number of elements that you hashed. Okay, and yeah, so this is just a scaling of that. So here I return 2 to the n over min hash. And so let me just give you kind of a very general recipe to convert this F0 estimation algorithm to a counting algorithm. So now I think of the set of distinct solutions of the Boolean formula as forming my stream. Okay? And what I want to do again, I mean, so really, my model counting is just finding the number of distinct elements in the stream, where the stream consists of the solutions to this Boolean formula. Okay? And so the formula phi can be viewed as some succinct representation of the stream, okay, of AU, which is a set of distinct elements. And now what we want to do is we want to capture the relationship between, so there's some relationship which captures this relation between the sketch S, the hash function H, and the set AU. Okay, so there's some invariant which holds at each step. Right, and then there's some process which takes so given an an S in which this invariant holds, there is a process which retrieves an estimate of what we want from the sketch. Okay, so let's maybe for concreteness, let's again turn back to this minimum algorithm and see what the relations are. Yeah.
What is U and what is this?
So U just indicates the distinct elements, the unique elements in this. Okay, so here, okay, so what is the invariant? So the invariant is that, so the sketch here just consists of, I mean, if you have just a single hash function, it just consists of the minimum hash value, right? So the relation that we are trying to capture is that S is the minimum of all the hash values of the elements in the stream. Okay, and so now in our case, the stream consists of a set of solutions. Right? So the sketch that we want to maintain is minimum over all the solutions of the hash values of y. Okay, so minimum is over y being solutions of phi of h of y. Right? And okay, so this is the key thing. So what we want is that we would want to, so if we want to actually be able to use this F0 estimation or streaming for model counting, we somehow need to be able to approximate or I mean retrieve this S efficiently. Okay, okay, so yeah, so here is where I'll just give a very high level sketch, and I mean so for students in the audience, you should actually be able to fill in all the details. Okay. So what is going on? So remember again, H is just described by a linear system of equations. Okay, and so just for concreteness, let's for example turn to phi being a DNF formula. So phi consists of a set of terms. Okay, so one term looks like x1 and x2, another term looks like x2 and not x3, things like this. And so what you would want to do is, so just look at one term individually. Okay, so this term fixes some of the variables. So for example, if the term is x1 and x2, then it fixes x1 to be 1 and x2 to be 1. Okay, so now what we would like to do is that, so y has x1 and x2 fixed to be y1 and y2 are fixed to be 1, and I'm looking at all the possible h of y. Okay, so h again, so h of y is a linear subspace. It's a mapping of a matrix times y. So I'm looking at all the linear images of this y where the first two coordinates are fixed. Okay, and I'm looking at the lexicographically smallest solution to the rest of the vector. And you can do this by a prefix search kind of procedure. So you can find, so once you have, so if you have n, so you have some number of bits remaining to fill, so you can search prefixes to find like the smallest prefix, which actually, for which there exists a solution to the linear system. And so this can be done using Gaussian elimination. Okay, so this kind of very high level sketch. But once you use the fact that H is described by a linear system, you can do, so for DNF formulas, for example, you can just do this kind of prefix search procedure to find the lexicographically smallest solution in the polynomial time. Okay, and generally we don't have DNF formulas. You have some general Boolean formula. So what you can do is you can again do the same thing, but using an NP oracle. So again, like in an NP oracle, you can encode these constraints about the prefixes being some particular value, and then you can ask what is, does there exist a solution with that particular prefix? And you can keep fixing the prefix one bit at a time and find the lexicographically smallest solution. Okay. So you can, yeah.
H was the identity. This would just mean give me the lexicographically smallest solution to B.
Yeah.
But now you're saying, okay, not the standard lexicographic, but like under the image of some
of a linear map, and you can use Gaussian elimination to always find if there exists. Yeah.
Is it like interesting to actually study the exact number of queries, like the finer analysis?
Yeah, actually we do that. To find and it match. Yeah. So we get an algorithm which matches the best known algorithm for DNF counting. Okay. Right. So okay. But the takeaway from this slide is that there is an efficient way. So if you care about DNFs, there's an efficient way to maintain the lexicographically smallest, lexicographically smallest hash value among the solutions to a DNF term and then to a DNF formula. And if you have a general Boolean formula, you can replace Gaussian elimination basically with NP oracles. Okay. Okay. Let me also tell you about a different algorithm, and again there will be a similar solution. So here, this is another algorithm for F0 estimation. So here, what you are doing is right. So okay, so let's look at this simple pseudocode. So again, you have the same structure. So for every element in the stream, this is some processing which updates the sketch. Here, the sketch is described by this cal b, and ultimately there is an estimator which involves the size of this b. So what is this doing? So basically, here I'm checking. So here L, there's a number L here. So this L is checking if the number of hash values which have L many trailing zeros. So I want the number of AIs whose hash values have more than L many trailing zeros to be less than this threshold. Okay. So I check if AI has at least L many trailing zeros. Okay. The hash value of AI has L many trailing zeros. And I add that to B. If it does, I add that to B. And if you have more than thresh many elements that you have processed, which have at least L many trailing zeros for their hash value, then you increment L by 1. Okay. So I filter. So basically, I remove all those AIs which don't have. So now L becomes L plus 1. The original, so it's incremented. So if the elements which have been stored in B, they don't have this L plus 1 many hash trailing zeros in their hashes, I take them out. Okay, and so the size of B now becomes smaller potentially, and you keep doing this until the size of B becomes smaller than thresh. Okay, so L is at the end of the stream, L is the smallest value of is the smallest value such that there are at most thresh many elements in the stream whose hash values have L trailing zeros. Okay. Okay. And again, right? So I can encode the relation in a very explicit way. So here, S, the sketch consists of this L and this B, and right. So basically, so B, as I said, is all the elements in the stream whose so if you look at the pre-image of those elements which end with L zeros, right? So B is the pre-image of AU intersection all the elements, all possible elements whose hash values end with L zeros. And if you take L minus 1, then so L is the smallest such, right? So the number of elements whose hash values ended with L minus 1 zeros would be more than thresh. Okay. Okay, and again, so if you want to apply this to model counting, so if the stream is the set of solutions to some formula phi, you would do the same thing, but here the AU would become the solution of phi. Okay, and so again, what you want to do is you want an algorithm which would maintain this invariant. So each time, so given phi, you would be able to construct this B efficient. Okay, and again, for example, if you have if phi consists of a DNF formula, what you can do is you can process a term by term. So each time a term comes, you can check how many solutions there are which satisfy that term and which have so many trailing zeros, and you can keep track of this B in that way. Okay, okay, and you can do the same thing for a general formula using an NP oracle instead of looking at it term by term. Okay.
What is thresh again?
So thresh is a threshold that you set. So it depends on the epsilon and the delta that you're using for the approximation. So it's typically like 1 over epsilon square log 1 over delta, something like that.
In general, this is like maintaining a statistic which, when scaled appropriately, would give you the number of distinct elements.
Right, exactly.
Yeah.
I mean, in analyzing the, so I mean, in analyzing this, I mean, so there's the expectation. You also care about the variance, and you need to show this high probability bound that with probability 1 minus delta, the output of this algorithm gives you the right thing. But here, what I'm just describing is this recipe for converting the streaming algorithm to a model counting algorithm. Okay, but the same guarantees then go through for the model counting algorithm. And this actually corresponds to a previously discovered algorithm for model counting called approxMC. But this connection between the streaming algorithm and the model counting algorithm was not noticed earlier.
In fact, even leveraging the fact that there are two-wise independent hash functions that are really space-specific. Then you could actually, in the first main example, you are actually using
right.
N by
and
not the modulo P.
Yeah. So, for example, there are some algorithms. I mean, F0 counting algorithms. So there's a theoretically kind of a space optimal F0 estimation algorithm due to King, Nelson, and Woodruff, but that doesn't use pairwise independence. It uses higher order independence. So, meaning instead of linear functions, you have polynomials. And actually, there we don't know how to, for example, in the minimum algorithm, we don't know how to get an efficient algorithm based on that, because basically we don't. I mean, so you use Gaussian elimination to check satisfiability for giving some particular prefix. We don't know how to implement the same thing when you have polynomials instead of XORs. Right. So like I mentioned, I mean, so if there is specific structure, like for example, for DNFs, it gives you a fully polynomial time randomized approximation scheme. And I mean, these are distinct algorithms. They are very different from this classical Cart-Luby algorithm based on importance sampling that you see in standard randomized algorithms class. But it seems equally simple and has same guarantees. You can also get something for other classes like unions of XORs. And we actually have some, some theoretical connections between these NP query algorithms. So the guarantee is that polynomial in n space algorithms and streaming translate to polynomial in n NP query complexity algorithms for model counting, where n is equal to log of capital N. So capital N is the size of the universe. So this is independent of the actual algorithm that's being used. So the previous two examples I showed you were for specific streaming algorithms, but there's also a very general connection. And lower bounds for distributed streaming translate to lower bounds for distributed DNF counting. For reasons of time, I won't really go into the distributed setting, but there is previously studied kind of this distributed functional monitoring setup where the stream once is partitioned into a set of different parties, and there's a monitor which gets information from the different parties. And there's also a similar setup for model counting, and there's a similar connection between them.
Sorry,
Yeah.
I might have missed this,
Yeah.
but is the Karpov-Matras algorithm interpretable as a...
Not really, no. Yeah. Yeah, maybe another remark is that instead of counting, another problem that often comes up is sampling. So you want to sample, say, uniformly or approximately uniformly a random satisfying assignment. And we show a similar connection between the sampling question for Boolean formulas and L0 sampling for streaming. So this was also another question which had been studied in the streaming community. But again, this connection was not noticed before. We show there's a similar connection between L0 sampling in streaming and the sampling question for the uniformly sampling from the set of satisfying assignments for Boolean formulas. Okay. We also kind of sketch the other direction from counting to F0 estimation. So really what we did, I mean, when we looked at this, so let's say again for DNF formulas. So really what we are doing is we are taking each term of the DNF formula to be succinctly describing a portion of the stream. So for example, so you have the whole DNF formula. So that gives you the full stream. So the set of all satisfying assignments for that formula. So a particular term gives you a subset of the stream. Okay, it gives you the satisfying assignments for that term. Okay, and we want to look at the union of all the different substreams. Okay, so the number of distinct elements in the union of all the substreams. So really, I mean, actually, I mean, it turns out that people in the streaming community have looked at such questions before, where each element in the stream is not really one single element, but it's a set of elements. Okay, so for example, the set of elements will correspond to something very natural, like in computational geometry, people look at this please measure problem, where you have rectangles which come in as a stream, and you want to count the number of lattice points which are contained in the union of rectangles. Okay, so you have a set of rectangles, and you're trying to count the number of, and you could also look at higher dimensional objects instead of rectangles. Okay, so as again, already right. So generally speaking, right. So anytime you have, so if you have these objects which are structured sets, and these structured sets are coming in one by one, so they are each element of the stream. Okay, so you can try to, and what you're interested in is the union of all these sets. Okay, so you can try to apply an F0 estimation algorithm, where I mean basically again, so now what you try to do is you try to kind of succinctly keep track of the sketch, right? So instead of, I mean, the clever part of the connection that I described before is that instead of actually enumerating over the whole stream, which is of exponential size, okay, we use the fact that the so the DNF has some special structure. So each substream consists of restrictions. So you, like, if the DNF term is x1 and x2, it consists of all the assignments where x1 and x2 are set to 1 and 1 each. Okay, so it's a succinct description of that part of the stream. So anytime you have a stream which consists of a sequence of structured sets, you can try to apply this same methodology, right? And you can see whether your sketch, and whether there's a way to update the sketch efficiently using the structure of the sets that come. Okay, so for example, if your elements correspond to intervals, so every element is an interval, AI to BI, okay, and again you are interested in the size of the union of these intervals. So what you can do is you can represent the interval using a DNF formula, okay, where the DNF formula refers to the bits that are used to represent this number AI and the number BI. And then you can use the FPGAs for DNFs that we described earlier to solve this problem. Okay? And this also gives improved algorithms for for the counting problems for intervals, hyperrectangles, and some other problems. Okay, Yeah, so just as a summary, so we talked about this connection between F0 estimation and counting and F0 estimation, where basically, so the second connection again is recasting counting problems as solving model counting over formulas, and then applying our algorithms or other previous algorithms for model counting. And like I said, I mean, these algorithms also, I mean, this connection also extends to sampling, where now the connection is between L0 sampling and sampling from the models of the formula. All right. Okay. Yeah. So some future directions, we're actually looking at practical scalability of these new counting techniques. So I'm not actually very directly involved here, but there's a research agenda which is called Beyond NP. So instead of taking NP Oracle calls for granted, you are now looking at the complexity of solving these counting problems. Okay? And as I said, for database applications and some other areas, I mean, these model counting problems are very fundamental. So one really cares about efficient algorithms for approximating solutions to Boolean formulas, approximating number of solutions, and we are kind of seeing whether this connection that we have found here, as well as looking at other F0 estimation algorithms. So for example, in practice, people use this algorithm called hyperlog for F0 estimation. And again, one can create a model counting algorithm based on hyperlog. And it seems from preliminary experiments that it is, I mean, it does as well as the state of the art. And so we are exploring further. In general, it's an interesting technique whether you can use ideas from, okay, yeah, I'll talk about the second point later, but in general, it's an interesting direction. I mean, whether there are other connections between streaming algorithms and counting problems, given the prevalence of hashing in both the different communities. Yeah, there's a second bullet here which talks about sparse hashing techniques. So in the model counting community, people have used hashing, so special hashes where each hash consists of XORs of only a small number of elements, not n over 2 elements like we discussed before, where each XOR consists of, so what I described before, in each XOR you choose whether to include the variable in the XOR with probability half. Okay? So you can look at sparser XORs where you are XORing together smaller number of variables. And there are formal guarantees in the model counting community. We are seeing whether some of those ideas can be transported to streaming problems. Okay, so I'll stop here. Thank you for your attention. Yeah.
So the second result is about Cleese measure, or that one example is Cleese measure.
Right. Yeah.
What is the runtime guarantee, like n power d or something?
No, it's polynomial in n and d. Yeah. Yeah.
So what was the best known before?
Yeah. See, I don't remember off the top of my head, but yeah. I mean, yeah, I'm hesitating because there was a previously published result which turned out to be incorrect, and it was not. I mean, so they claimed polynomial time, but it was not polynomial time, and yeah. So I mean, so we resolved that bug and also get polynomial time.
Yeah. Other like FP estimation or other norms, do they have any interpretation in the model?
It's a very interesting question. I mean, so one could look at, right, so there basically you're counting, right, I mean, like you're looking at not just counting the number of distinct solutions to some formula, but maybe weighted by how, yeah, so I don't actually know. Yeah, interesting.
And also, like, you said sampling also.
Yeah.
And so you could, does that connect to all these, there's like sampling techniques are quite like the Sinclair, Jerome kind of work is it's a very different methodology. Like if you want to see
right, so those are for combinatorial problems. Yeah.
So again, going back to they use these Monte Carlo, like these chain methods. So that's quite an interesting connection that you can use those sorts of those hammers in this streaming work.
Yeah, I think it's we have not really explored much, but I think it's yeah, these are very interesting questions. Whether I mean, right, so this sampling and hashing is kind of very recent. It's in submission, but right, I think like if you specialize it to particular combinatorial problems, if there are any new algorithms which come out of this connection, I don't know.
It's also the similar situation with weights, right? Like that's so that like you might have if you associate a weight with each AI, that will probably naturally just incorporate algorithms. So want to find number of solutions of P to analyze more than one.
I see.
I mean, in some sense, so if I go back and look at the way you formulated it,
right,
it's actually like an optimization, minimize over solution of P. So there's a finite to quite large set.
Right.
You're minimizing some linear function on top of that.
Right.
The thing now, okay, on top of the selection effects, I add additional constraints to it, like this linear constraints.
Right. I think
Gaussian elimination work or
yeah, I mean like the linear constraints we were talking about were mod 2,
yeah,
whereas you were talking about
yeah, more
general constraints. Yeah, I mean,
I don't want to just pick, if it's mod 2, I could envision just changing P.
right,
Right, like add another clause that says that only even parity
right,
solutions.
right.
Not that, but I actually want again like the connection being like, for certain class of maybe combinatorial problems.
Right.
P incorporates independent sets.
Yeah, I'm not sure. Yeah, we can talk about that.
So problems like that are like counting matchings and all.
Right, not like these other constraints which come in.
Yeah.
So, right, I mean, it could be that there are other non-trivial algorithms to maintain the sketch using the structure of that problem.
Right.
Okay, thank you.